Okay, thank you very much for the introduction. I'll also start the timer. So I changed the title of the talk a little bit. If time permits, I will maybe briefly talk about learning graph runs from data as well. But the main talk is about learning quadratic embeddings for nonlinear dynamical systems. This talk might be a little bit more controversial because it's not directly related to Koopman operator theory, but in a way it also is, as you will see later. And the question is really how this quadratic embedding framework can be used. What are the advantages and disadvantages? I should point out that this is really work in progress and there are lots of open questions. The first part is joint work with Joel, Pascal, and Gonzi. And the second part is joint work with Jason Bremberger. If I have a couple of minutes, I might quickly show you how you can define transfer operators for graphons. Graphons are continuum limits of converging sequences of graphs. So what happens if you let the number of graphs of nodes go to infinity, then you obtain a graphon. And you can define random walks again, transfer operators. You can use this for spectral clustering. And you can also learn graphons from data. If you have random walk data, you can learn the underlying transition probabilities and the graphon itself. And this is also work in progress. Okay, so I don't think I need this motivating slide here. There are lots of different applications we've been working on in the last couple of years. We've typically used, for example, Koopman operator theory for molecular dynamics problems, where we are interested in finding conformations, for example, folded and unfolded states of proteins. We have applied Koopman operator theory to fluid dynamics problems, where we are typically interested in finding slowly evolving spatial or temporal patterns. You can use this for finding coherent sets in the ocean, for example, eddies or gyres. We've applied this to quantum mechanics problems. There are close relationships between Koopman and Schrödinger operators. And then, of course, you can use it for learning almost invariant sets, for system identification. This is what I will be talking about today. It has been used for control as well. And you can also define transfer operators for graphs. And this graphon approach that I just mentioned is basically an extension of this work on graphs to the continuum limit, where you then obtain a graphon. Okay, so I will first talk about quadratic embeddings of nonlinear dynamics. And the idea is that you have an autonomous ordinary differential equation, which is given here by x dot is equal to f of x, where the state space is lowercase n-dimensional. And we want to embed this n-dimensional dynamical system into a higher space, but we don't want to make it linear in this case. In this case, we want to make it quadratic. This is a framework that has been used in the model reduction community. And the assumption here is that f consists of elementary functions. And elementary functions are, for example, polynomials, trigonometric functions, exponentials, all kinds of combinations or compositions of these functions, and also rational functions. So basically, any smooth dynamical system is a composition of elementary functions. The only thing that is not allowed is something that is defined only piecewise. This would make it a little bit more complicated. Now the goal is, again, we want to embed our system into a higher dimensional space. This is here denoted by capital N. So we are going from a lowercase n-dimensional space to a capital N-dimensional feature space. And we want to find a transformation of the dynamics, which is here denoted by phi, so that the dynamics become not linear, but quadratic in this case. That's the main difference here. So the goal is to find matrices A, B, and this vector C, so that the dynamics in this lifted space are of this form. You have here Z dot is equal to some matrix A that we want to identify. Then this is the Kronecker product of Z and Z. This contains, for example, Z1 squared, Z1, Z2, and all kinds of combinations of these terms. Then you have all the linear terms and the constant terms here. And the question is, how do we find the optimal matrices containing these coefficients A, B, and C so that our dynamics are ideally quadratic, or at least as quadratic as possible? So we formulate this, as, of course, as an optimization problem, and then we want to determine the best possible embedding. Another assumption that we make is that there is a matrix G so that we can write the original state space variable X in terms of the Z variables. This is very similar to this full state observable assumption that you can represent the full state observable in terms of your dictionary. This is very common also, for example, for EDMD-based methods. And the best way to do this is just to add the full set observable itself to the dictionary, and then this is trivially satisfied here. Okay, so this is the goal. And this quadratic embedding always exists for these smooth dynamical systems, and it's always finite dimensional. This is really the main advantage here. So we are not going to an infinite dimensional space, but the dynamics really are always quadratic in a finite dimensional space, provided that this condition here is satisfied. Also, just to show you quickly how this approach works, we just consider a very simple nonlinear dynamical system of this form. So this is just a one-dimensional ODE, and we want to make this quadratic now. And the approach is very similar to what we do in Koopman operator theory as well. We just define new observables. So I here just define x2 to be exactly the right-hand side. there are different ways to go about this. This approach is not really uniquely defined, and you can do this in slightly different ways, and you obtain slightly different quadratic models at the end. But so for now, we just define a new variable x2. And then, of course, we have to use the chain rule to compute the derivative with respect to the time t. So now we can write x1 dot as x2, and then we have to compute the derivative of x2 with respect to the time t. Then you just have to apply the chain rule. So you get -1 multiplied by this function squared, multiplied by e to the power of x1, multiplied by x1 dot, but x1 dot is now x2, so you get this expression here. So now we have a cubic term and still some exponential term we want to get rid of. So we define a new variable. Now the third variable is defined to be e to the power of x1. And again, we can rewrite now x2. So now x2 is at least of polynomial form. It's not quadratic yet. And then we have to compute the derivative of x3 with respect to the time t. So you get x3 dot is x2 multiplied by x3. And then you just continue. Now we want to get rid of this cubic term to make it really quadratic at the end. So we define a fourth variable x4 here. And again, we just follow the same steps. Now we have a quadratic term here. The third equation is already quadratic. After applying the chain rule again, we get also a quadratic equation for x4. So now we have quadratic equations for all of our variables, and we are done basically. We have identified a quadratic model in a four-dimensional state space instead of now using this one-dimensional highly nonlinear ODE. And this approach goes back quite a long time. It was even discovered before the Koopman operator was defined. So the first paper that talks about these quadratization techniques was published, I think, in 1902 roughly. So this is the general idea. And I will just use this benchmark problem that we found in a paper by Pavan Goyal and Peter Benner later as well. So here we again have a nonlinear dynamical system. It's in this case a rational system. And you can show that if you use these three observables here, you can make the system quadratic, and the quadratic equation that you get afterwards in this augmented state space is shown here. And now later we want to learn this, of course, from data. We assume again that we have trajectory data and we want to identify this embedding. But for this one, we can just do this analytically so that we have a reference later. And then you can see that the matrices are sparse. There are lots of zero entries here. The matrix B is even completely zero in this case, and the vector C as well. This corresponds now to this dynamical system. And here in this case, the matrix G is just the matrix 1, 0, 0, because the first variable is x here. So if we want to retrieve x, we can just use the G matrix here, or the G vector in this case. Okay. Just to compare this with the Koopman framework here, often in the literature you find these systems that are nonlinear, but you can make them linear in a high-dimensional space. A typical system is of this form. For example, here we have x1 dot and x2 dot. It's now of fourth order in the first equation, and it's just linear in the second equation here. And if we now define a new variable, x3, to be x2 to the power of 4, then we can linearize this system. So in this case, we can find a Koopman invariant subspace, and we can easily compute eigenfunctions of the Koopman operator by computing left eigenvectors of this matrix. And we can also compute eigenvalues and so on. And then we can use the properties that products of these eigenvalues, products of these eigenfunctions again, and so on. So in this case, it's possible to linearize the system. But if you make the system slightly more complicated by adding a second term, so instead of only 2x2, we consider now x1 plus 2x2. If we would try to follow the same approach, what happens is you define a new variable, you apply the chain rule, then you get a new equation for this new variable, but the new variable again contains terms that are not contained in your dictionary yet, so you have to continue. And in this case, this process does not terminate. So you need basically more and more variables, and you cannot really find a closed representation, a linear representation using these monomials. And if you use the quadratic embedding approach, you just have to define one additional variable, and then the system is automatically quadratic, and you are done. So this is just to illustrate the differences between these two approaches. But of course, we cannot easily talk about spectral properties here, but I will get back to this later. So now the question is, how do we learn this quadratic embedding? We assume again that we have a fixed set of dictionary functions. Of course, you can later also use machine learning or deep learning to find the optimal dictionary at the same time. And there are papers about that as well, for example, by Peter Benner and Peter Benner's group. So assume now that we have trajectory data. This is now very similar to the Cindy approach, and I will compare this to Cindy, of course, as well later. We assume that we have training data, we have the time points xk, and we have the corresponding time derivatives xk dot. And of course, you can approximate them using finite differences if you like. If you have small time steps, this typically works quite well. And then we just transform our data set. We use our dictionary to map our data to this higher dimensional feature space. And then, of course, we also have to compute the corresponding time derivatives. This is, again, just using the chain rule. So that means we also need the derivatives of the basis functions. But here we can just use automatic differentiation. So this can be also easily computed. And then we define a loss function So we want to find the best matrices A, B, and C so that the model becomes quadratic. And the loss function is just here the reconstruction error. We want to find the matrices A, B, and the vector C in such a way that this prediction of the derivative is as accurate as possible. So this is just a normal least squares minimization problem. And in order to simplify this and in order to compute the optimal solution, we write this in matrix form. So we define all these data matrices here. Z1 just contains the data points themselves mapped to the higher dimensional feature space. And then this matrix Z2, this contains all the quadratic terms. So this contains Z1 and then the Kronecker product with itself and so on. And then the last matrix, this is very similar to Cindy as well, just contains all the time derivatives here. So now we have all these data matrices, and then we can write this loss function that I defined here in a more compact way like this here. And the advantage is now we can compute the derivatives of this function. So we have to minimize the Frobenius norm here with respect to A, B, and C. We just compute the derivatives, and then we check under which conditions the gradients are zero or the derivatives are zero, and these are our optimal solutions. This is now shown here. So after computing the derivatives of this loss function with respect to these three variables A, B, and C, you can see that we get a system of equations. And what you can also see is that the systems, the equations are decoupled. Basically, we can just identify the rows of the matrices A and B and the rows also of this vector C independently. And you get this system of linear equations here. I just call this matrix R because later we want to consider the infinite data limit. So the question is what happens if you let the number of data points go to infinity. Here you have all of these matrix products. And if you let the number of data points go to infinity, these converge to integrals or inner products between basis functions. So this is a very simple best approximation. And I will also show this later, how this is related to Cindy. So we want to see what happens now later if R, the number of data points M goes to infinity and what kind of solutions we really get then. But we call this approach QENDI. This is now quadratic embedding of nonlinear dynamics, closely related to Cindy. And I will show this also in some examples later. So just to get back to this very simple test problem that I defined earlier. So this is now this rational system with this very simple right-hand side. We know that there is a quadratic embedding if we use this dictionary that I showed before. And in this case, if we apply our method, then we get this system of equations. It's not exactly what we derived before, but it's equivalent. So it is really identifying the correct dynamical system in this case. And the training data is just this gray dots here. And the derivatives are denoted by these slopes here. And then we apply the learned dynamical system to a new initial condition. The new initial condition is shown here. And then you can see the true solution is this dotted line. And we really identify the correct dynamics. And also the equation here is really the dynamical system itself. If we now use, for example, this G matrix to project this back onto the original state space, we really get exactly the right equations. And the question is, of course, what happens now if we add more and more data? This is shown here. So I mentioned already that if we let the number of data points go to infinity, then all of these matrix products converge to weighted inner products. And you can see here that these weighted inner products are just depending on the basis functions. And we have also these quadratic terms here. Since we are trying to learn a quadratic embedding, we're not using the feature space itself only, but we are also computing implicitly products of all these functions. So basically, implicitly, we are just generating a higher dimensional feature space than just using the dictionary itself. You can see here that this is what we get in the infinite data limit. And you can show that this is a best approximation. But here we are using this, we call this quadratically augmented dictionary. We're using all products of the basis functions themselves, and this constant function, this corresponds to this vector C at the end. And then you can also show that you get the typical Monte Carlo convergence here. If you let the number of data points go into infinity, you get this O of m to the power of -1/2 convergence to this true matrix R star. But I should point out here that we don't really need this infinite data limit convergence here. Typically for a couple of data points, since we just have to estimate some parameters, it works already really well. So you can see here, this is the initial condition now, and we apply our approach to this damped nonlinear pendulum. If we use 6 data points, then you get this blue curve here. It doesn't look correct yet, but at least the shape is roughly the same. If you increase this to 8 data points, you get this red curve. And then finally, if you use 10 data points, you can see that the yellow curve coincides with this dotted line, which would be the true solution here. So with just a very few data points, you can really learn this quadratic embedding, and you can make predictions, and you can also really extract the governing equations in this case. But of course, this depends on the dictionary that you are using, and you have to, of course, ensure that the dictionary is sufficient to really learn this quadratic embedding. And I will show some examples later what happens if this is not the case. So yeah, I mentioned already that this approach can be viewed as a best approximation. Best approximation simply means we have a Hilbert space of functions, and we consider just a subspace that is spanned now by our dictionary functions, and we want to find the best approximation in this Hilbert space that is contained in the subspace. This is a typical optimization problem. What you have to do is you just define this matrix A that contains all these inner products between all the basis functions. You define this vector B here, and then you just solve this system of linear equations. And this might be, the matrix A might be singular, or yeah, and then this could cause problems, but then we would just use the pseudo inverse and we get the correct matrix, sorry, the correct solution containing the coefficients alpha here. And this is just the difference between discrete best approximation and continuous best approximation. If we let the number of data points go to infinity, then we obtain this here, but that's all. And just to show that Cindy is doing exactly the same, if you're familiar with the sparse identification of nonlinear dynamics approach that was proposed by Brunton et al. In 2016, you can write Cindy in exactly the same way. We define the data matrices containing the time derivatives. This is here denoted by x dot. We define then this matrix phi of x, which contains the transformed state space variables, and then we can write the loss function in this form here. So in this case, we want to find the matrix xi so that this loss function is minimized, and this is exactly what Cindy does. In the paper, they add sparsity constraints. Of course, you can use L1 regularization or iterative hard thresholding. I'm just omitting this here for the sake of simplicity so that you can really see that this is very closely related to the Cindy approach. And then Cindy is just in the infinite data limit also converging to a best approximation where you have here inner products between the basis functions only, but you don't have all these higher order terms that we implicitly construct. So you can see that Cindy is just a best approximation of the right-hand side F of our dynamical system. And to compare these two approaches, we again use this very simple rational system. I already mentioned that if you use this dictionary here, then this is sufficient for learning quadratic embedding. Then we use a slightly different dictionary by just adding one function. And then the third dictionary that we are using is just monomials here. We know that monomials are not sufficient for learning a quadratic embedding. And it's also not sufficient for representing the right-hand side in terms of the functions here. So if you look at the errors here that we obtain, if we use our approach, this Quendi, then you can see that if we use this dictionary containing these three basis functions, the error decreases very quickly, goes to roughly machine precision, and then we identify really up to, of course, numerical errors, the correct dynamical system. If you use Cindy with this dictionary here, it does not work. You can see that the error does not really decrease and does not go down to at least numerically 0. And this is because the right-hand side cannot be expressed in terms of this dictionary here. If you add an additional function, then Cindy works as well. So now if you take these 4 basis functions here, you can write the right-hand side in terms of these basis functions. And then you can see, if you then compute again the error, both errors converge roughly to 10 to the power of minus 15. So the models that we identify are really very accurate approximations. And then the last dictionary that you see here is unsuitable in general. So we cannot approximate the right-hand side in terms of this. And we can also not learn the quadratic embedding using these basis functions. What you can see is that the error does not really decrease. So it's stuck here at 10 to the minus 2 or 10 to the minus 4. And you can also see that this Quendi error is a little bit lower, but that's only because we are generating higher dimensional feature space. So that's why we have more flexibility to approximate this right-hand side. We applied this to a slightly more complicated problem. This is the so-called Thomas attractor, but we modified it a little bit. So if beta is equal to 0 here, this is the Thomas attractor, and you can see the dynamics here. If we add this additional term, the dynamics are a little bit more complicated. This is just to visualize that this is a chaotic dynamical system here. And we consider 2 different test cases. The first test case is shown here. Here we set beta to 0. That means that all of these terms drop out. And then if beta is equal to 0, this dictionary is sufficient for learning really a quadratic embedding. We need a 9-dimensional space. And in this 9-dimensional space, the dynamics become quadratic. If beta is non-zero, then this is not sufficient, and we would need at least a 15-dimensional space to find the right quadratic embedding. So that's why we consider these 2 different test cases. And you can also see numerically what happens if you consider these test cases. The first test case is, here we know that the set of basis functions is sufficient for learning a quadratic embedding. You can see that the matrix A that we learn is quite sparse. Almost all of the entries are 0. The matrix B is also sparse, and the vector C is in this case 0 because there are no constant terms. And then Cindy works in this case as well. And you can see that we can identify really the correct dynamics, and we can make long-term predictions over long periods of time. This is for the case where the dictionary is sufficient. If we consider the test case 2, where the dictionary does not contain enough basis functions to represent the dynamics in this quadratic framework, then you can see that the matrices are non-sparse. And also now the vector C contains entries and the matrix B is also non-sparse. There's no difference between system identification and system or approximation of the dynamics. So here sorry, can you make it full screen again? Thanks. So here we really identified correct dynamics, but if you go to the next system, here we can only approximate the dynamics. The feature space is not powerful enough to represent the dynamics accurately, but at least we can find the best approximation in this space. And this is what you can see here. So if we use our approach, then we can typically make predictions that are more accurate for a little bit longer. But at some point, these models also, of course, become unstable and might not be able to predict the dynamics correctly anymore. But this is at least more accurate than if you would just use Cindy, for example. This is what you see here. Just to show you one last dynamical system, here we considered this so-called von Karman vortex street that you've probably seen already before. The dynamics are shown here. At the beginning, you have this transient phase, and after a while, this periodic vortex shedding starts, and then it's just switching between these different modes here. And you can show that if you apply a principal component analysis, this system is roughly three-dimensional. So there are three dominant singular values here, and then we project this onto the dominant singular values. This is the first principal, singular vectors. This is the first principal component, this is the second principal component, and the third one, which corresponds to this transient phase at the beginning. And then we approximate the derivatives now really using finite difference approximations because we don't know the true equations here in this case. This is then our training data. This is the dynamics in this principal component space, the projection onto this three-dimensional space. And here we again try to learn the dynamics, and we compare our method with a deep learning-based technique. This is the framework proposed by Peter Benner and his group. And you can see that our method, here we just used linear basis functions, is more accurate than a deep neural network. So with just the full set observable as our dictionary, we can make really long-term predictions. This gray area here, this is the extrapolation phase. You can see that we can really represent the dynamics, and we can also extrapolate, and we can really predict the evolution of the dynamical system, also here in this case over long time intervals. I think I will stop here. I have 2 or 3 minutes. I can just very quickly show the joint work with Jason Bremberger, where we are trying to define transfer operators for graph fonts. I will show only the idea and then some numerical examples. So a graph font is nothing but a function from this interval 0 to 1 times 0 to 1 to 0 to 1, 1. And you can view this as a generalization of a weighted adjacency matrix. So this function W tells you how likely it is that the edges are connected. For example, you can take 2 arbitrary vertices x and y that are contained in this interval from 0 to 1, and they are connected if the function W here is larger than 0. And then just like for graphs where you define in and out degrees, we define here in and out degree functions. For the matrix case, these are just the row sums and the column sums. But here we now have to compute these integrals. And if the graph is symmetric, which means the W of x, y is the same as W of y, x, then the in and out degrees are the same, and we just call this d of x. And then we can define a transition density function, which tells us that if I start in x, how likely it is to jump to y. This is what we need to define a random walk. So the probability density function is just given by the graph on itself divided by the out degrees, so that this is really probability density function here. And then we can generate random walks. And given, for example, an initial condition xk, we can sample the next position by just sampling from this distribution here. And here we can use something like rejection sampling to generate random walks. And what you see is that this looks very much like stochastic differential equations. Here we constructed the graphons in such a way that they have clusters, and later we want to identify these clusters. So here you would have 3 clusters, one here, and one smaller cluster in the middle. And we want to use now these random walks to identify the clusters. So what we do is we define transfer operators, and then we can compute again dominant eigenfunctions. There's a spectral gap that typically tells you how many clusters there are. And we also extended this to the non-symmetric case. This is a symmetric graphon, and you can see the random walk has this typical metastable behavior. It stays for a very long time in one cluster, then it jumps to the one in the middle maybe, then it jumps to the other one, and back and forth. And this is again encoded in these eigenfunctions and eigenvalues. So I will just stop here, and thank you very much for your attention.